Department of Collegiate Education, Digital Learning. Welcome to the video session of BSc third semester DC Circuit Analysis. The video is presented by Savita S. So in this video, we will be discussing about Thevenin's theorem, steps involved in Thevenizing a circuit, explanation with a solved problem. So electrical networks are usually complicated interconnection of several circuit elements with sources. So in such a scenario, determination of output current and voltage becomes difficult. In a complicated circuit, it's always difficult to find the output current. So Thevenin's theorem is used to simplify complicated circuit or complicated electrical networks. So using Thevenin's theorem, we can simplify complicated networks. We'll see how to Thevenize a circuit. So first we'll see what is the statement, Thevenin's theorem statement. Any two-terminal bilateral network consisting of several fixed resistances and voltage sources can be replaced by an equivalent circuit consisting of single voltage source of EMF VTH in series with a single resistance RTH. So this is a diagram, a network. It's called as an electrical network consisting of several resistances and a single source. We can have several sources also. So all that is connected to a load resistance. So our interest is in finding load resistance and load voltage. So if the circuit is complicated, it becomes difficult to find the load current and load voltage. So what we do is, using Thevenin's theorem, several resistances are replaced by a single resistance called as Thevenin's resistance. Several sources are replaced by a single source called as VTH, Thevenin's voltage. So instead of many resistance, we can have a single resistance and single voltage. Then the circuit becomes a simple circuit which gives rise to same IL and VL as we had in a complicated network. So the steps involved in Thevenizing a circuit are: remove the load resistance and calculate the open circuit voltage across the output terminals. Replace all the voltage source by their internal resistance and calculate the Thevenin's resistance. Draw the Thevenin equivalent circuit. Connect back the load. Measure RL and VL. So this is a complicated network. So first step is remove the load resistance. So we have removed the load resistance here. So there are three resistance, R1, R2 and R3. R1, R2, R3 with a single source Vs, and there is a load. We have to find out IL and VL in this complicated network. So first we will remove the load resistance. So it will look like this. In this circuit, measure what is the Thevenin's voltage. So as we have open circuited, it is easy to measure what is the Thevenin's voltage now. Next step is remove the load, remove the source, and looking back at the circuit from the open end. Look at the circuit from the open end and find what is the total resistance. That resistance is called as RTH. So from this circuit we are finding out VTH. By open circuiting the load, we are finding out VTH. By opening the load and removing the source, we are measuring RTH. Thevenin's, the effective resistance is called as the Thevenin's resistance. So use that in the second part of the circuit. That is, instead of having this source, you use VTH, and instead of having three resistances, we will have a single effective resistance RTH. So that becomes our circuit which replaces this circuit. So again our load is connected back to its position. We will find out what is IL and VL, output voltage and output current. That output voltage and output current will be same as what is given here, voltage, output voltage and output current. So this circuit is said to be electrically equivalent to this circuit. So this process is called as Thevenizing a circuit. So we will see how exactly we can Thevenize numerically by solving a problem, network problem. So here we have shown a network. The source is having a voltage equal to 48 volts with 3 resistance R1, R2, R3, 12 kilo ohm, 4 kilo ohm, 8 kilo ohm, and a load resistance equal to 5 kilo ohm. So first step is, before going to the Thevenin part, we'll measure what is the load current by using, this is not very complicated, sometimes we'll have complicated circuit. So we'll see first without Thevenizing what will be the current. So to find out that, we should find out what is the total resistance. So total resistance is, so these two are in series, 8 plus 5 is 13, that is in parallel with 4, 13 into 4 divided by 13 plus 4, that entire part is in series with 12k. So that resistance will be 15k, 15.06k. So total resistance of all this is 15.0k, that is connected to 48 volts. So main current is equal to 48 divided by 15.06, which is equal to 3.2 milliamps. Next we will find out what is the load current. For finding out the load current, we will use the branch current concept. We know what is the main current. Main current comes here, divides into two branches. So one in this and another current flows, that is called as the load current here. So IL is given by main current 3.2 into branch resistance of the other branch, okay, and sum of the resistances. So there are two branches here. This is the main current. Main current, when it reaches this point, it gets divided into two branches. One branch is having a resistance equal to 4k. Another branch is having a resistance equal to 8 plus 5, that is 13 kilo ohms. So 13k and 14k are the two branch resistances. Sum of the two branch resistances, 13 plus 4 is 17k. So total resistance of the branches is taken in the denominator. So main current into resistance of the other branch divided by sum of the resistance will give you branch current through the load, 0.75. So without Thevenizing, we have found what is the load current. Now we will Thevenize and see what is the load current. So to Thevenize, what is the first step? Remove the load resistance and measure VTH. So we have removed the load resistance, it becomes an open circuit and it is easy to find the current. So current is E by R. E by R is 48 volts divided by R. R is 12 plus 4, that is 16. 48 by 16 is 3 milliamps. There is no current in this part because it is an open circuit here. So 3 milliamps is the main current. So VTH means voltage across the output terminal is equal to current into this resistance. This current flows through this and a voltage is developed. That voltage is called as VTH. So 3 milliamps into 4 kilo ohm is equal to 12 volts. So 12 volts is the VTH. So next is remove the load resistance, remove the source, find what is the effective resistance at the output terminals, and you are looking at the circuit from the output terminal. So by looking back, whatever effective resistance you get, that is called as the Thevenin's resistance. So if you look back, then when you look back, this 12 and 4 are in parallel and that is in series with 8k. So 4 and 2 are in 12 are in parallel, that is in series with 8. So 4 into 12 divided by 4 plus 12 plus 8 will give you 11 kilo ohms. So whenever we have parallel connection, what is the formula? If R1 and R2 are in parallel connection, R1 into R2 divided by R1 plus R2. So whenever the resistances are in series, we add them. Effective resistance will be addition of all the resistance. Whenever resistances are in parallel, we take the reciprocal. 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3, like that. So we find the effective resistance across the output terminal by looking back at the by looking at the circuit from the output terminal. So this is effective resistance is called as RTH. So we have found what is VTH and what is RTH. We will connect that in the Thevenin's circuit. So VTH is 12 volts, RTH is 11 kilo ohm. Then we will connect back the load and measure what is the load current. So load current is 12 volts is the VTH divided by total resistance. 11 plus 5 is 16K is equal to 0.75 milliamps. So whatever current we are getting without Thevenizing the circuit, the same current we are getting after Thevenizing the circuit. That means this circuit is similar to this circuit. A complicated network can be simplified by applying Thevenin's theorem without changing the output current. So we'll keep the output current will not be affected without. That is why these two circuits are said to be similar. So we generally this Thevenizing circuit concept is used in complicated network. So this is an example problem when we have shown that a complicated network is equal to a simple Thevenin circuit. Thank you.